So first of all, thank you very much for coming to my last seminar. And so today I will conclude my seminar by proving property T for the tensor category associated, the representation category of the q-deformations of higher rank. And so I'd like to talk on all the argument, except some small calculations. So, yeah, but before that, I would like to recall our goal, and so what we have observed till the last time. So, our goal is to prove. Of course, our initial goal was to prove property T for certain tensor categories. And this is equivalent to, say, proving property T for the quantum double of a q-deformation of a quantum group. So the goal of today's lecture is to determine all reducible objects of the all reducible representation. Or reducible star representation of the quantum double. And again, this is same as saying determining the all reducible object in the categorical center of the representation category. And so this was our definition of the property T for, so that the isolation inside the irreducible object is our definition of the property T for tensor category. So anyway, so what I want to do is classifying all objects inside here. And so we recall this quantum double. So quantum double was So this was a star algebra. This is a star algebra generated by these two pieces. And with a certain commutation relation. And so this explicit description of the commutation relation is important in the computation of the intertwining operator. But so I will omit all the computation. So I just omit to introduce this explicit commutation relation. But anyway, so this is just algebra generated by certain algebra together with certain commutation relation. And then so our philosophy is. So these things should be seen as an analog of the D algebra, the quantized enveloping algebra over the complex semisimple D group. So these guys should be seen as the quantized enveloping algebra over the complexification of the D algebra, where the UQZ corresponds to the compact chart, and the function algebra corresponds to the quantized enveloping algebra of A plus N, where so GC is equal to G plus A plus N is the Iwasawa decomposition. Okay, so this is what I want to do, and so I need to say a few things on the quantized enveloping algebra also. So the quantized enveloping algebra, so this was a star algebra generated by certain element and together with the commutation relation. generated by AI, EI, and then phi. And so I do not repeat the commutation relation of these elements, but the important thing here is Ki should be seen as a certain kind of element like Q to the Hi, where Hi is the original, the generator of the original Lie algebra. So philosophically something like this. Oh, yeah, so yeah, plus minus 1, so plus minus Hi. And then here, the essential data for this UQG is more like a logarithm of the Ki rather than the Ki itself. So you can also take some fraction power of this guy to add the generator inside here. So one can also take replace AI, or one can also add fraction powers of AI, like this. I mean, in the this is important in the case of G's SLN, and to get some another star algebra, which is also more or less similar. I mean, it is more or less same as UQG itself. I mean, philosophically. Okay, and actually, so this is important in the in this embedding. So we have the embedding. So as I said, we have an embedding this from this into the twofold tensor product of UQG. But here, if you want to get this embedding, we need to take appropriate fraction powers of Ki inside here. And this precisely corresponds to the taking the weight lattice instead of the root lattice. I mean, so this Ki is due to the power of the root lattice, but you also need to take the one corresponding to the root weight lattice. But anyway, yeah. So with appropriate choice of this fraction power. And actually, this part gets more important in the classification, actually. So, okay, so now I want to start the classifying all reduced objects. And then, so if we recall the classification of the classical, complex semisimple Lie group. So first what I did was to prove the admissibility of any unitary, any reducible unitary representation. And the same thing holds for the this setting with the more or less same proof. So, I forgot to mention this. So most of the results are also independently observed by Christian Vogt and Bob Juncken. So, yeah. Anyway, yeah. So they, yeah. So here's then so what I wanted to talk is so if you have any reducible star representation of the any star reducible representation of this which decomposes into a finite dimensional one with respect to this on the Hilbert space. And so decomposes into Hilbert space which decomposes into direct direct sum representation of representation in representation category K2, which simply means all of Ki's acts as a positive operator and has finite K multiplicity sign. Which means so if you decompose into the irreducible finite dimensional representation with respect to UQG, then the multiplicities are all finite. So this is so as in the complex semi-simple case, this reduces the classification of certain analytic representation, unitary representation to the algebraic representation with certain invariant form, invariant linear form or the invariant inner product. So just in the same as in the classical case, so this reduces. So the classification of star-reduced representation into classification of reducible admissible representation. Admissible representation simply means the representation which has finite K multiplicity as in the classical case. And together with the determination, determine which of the irreducible admissibles which has invariant inner product. And for the first problem, actually we can give more or less the same same result as in the classical case. So as in the classical case, I introduced the classification of admissible reducible representation, or the more actually the structure of the space of the admissible representation in terms of category O. And the same thing holds for the quantum case as well. So I would like to recall the category O. So what was category O? Category O is so this is a category of. So yeah, so I introduced in the last lecture I introduced category O for the usual UZ, the usual inverse enveloping algebra, and so I want to introduce this for UQZ. So category of UQZ modules with, so more or less the same definition, so with the highest weight vectors. We start some certain finiteness condition. And then actually, so here's a very striking result by Tingoff and Kajdan. Actually, we do not use this result in the following, but I mean to give you some intuition about this category O over UQZ. So actually, when Q is transcendental over Q, and if you restrict the highest weight or the all-load weight to be rational, then So yeah, so especially so this is the case when you have no relationship between the weight, assigned weight and the Q. Then actually the category O for the UQG. So probably I should prepare another notation for UQG. Yeah, but anyway, so O for UQG is same as for the classical case. So this is really a categorical equivalent. I mean, linear category equivalent. So thanks for this result. So basically, we know all the result of the UQG. I mean, all of the result on the category O for UQG in terms of the category O for UZ. And actually, so we need a bit of this assumption. Q is transcendental, the weight is rational. And this is really necessary. And so this makes a bit of difference for the quantized case and the usual case. For example, so if you have some weight which sends HI to pi I log Q inverse, then if you want to send a Ki by this lambda, so Ki is of course Q to the Hi. So if you put so this on the Q of this power, then this is 1. So lambda sends Ki to 1. So basically the only different point appearing in the category O is basically philosophically this weight has a certain kind of period and periodicity. So in the imaginary in the imaginary direction. Depending on your choice of your first choice of the lattice you took to define UQG. Finding the choice of the lattice. Okay. Now anyway, so yeah, basically so yeah, again, as long as Q has no relationship with the weight, so we basically know, I mean, we philosophically basically know, I mean, it hasn't been proved, but I mean, yeah, so we basically know anything about category O in terms of the classical case. And I want to use this to investigate our target category admissible representations. And then in the classical case, this is related by the theorem by Drinfeld, Drinfeld, and Enright. And what? Yes, right. Yeah. So in the quantum case, there's a similar theorem by Joseph and Letzter. So you take arbitrary weight, which is dominant in some sense. So actually the problematic thing here is, I mean, so we have a period, so you need to take this period into account. But I mean, so if for example, if the real part of the lambda is dominant, then we have a functor from category O with a compatible weight with lambda, which simply means that, so again, this is weight minus lambda is inside P. I mean, so the weight appearing in the module in category O has an integral difference from lambda to the admissible representation of GQ, which simply means this thing, so the representation of UQ equals OKQ, which decomposes into a direct sum of the finite dimensional reducibles with finite multiplicity with respect to QG action, with a fixed right central character. So this is a fixed, I mean, so the central character lambda. So again, so this is really the same as, more or less the same as the classical case, and the right central character is nothing but the center of UQZ sitting in the right tensor component there, which actually lies in the small algebra there. So I mean, so the center, I mean, one tensor center acts as a scalar on a reducible representation. So we fix this scalar to restrict the category. So basically, what we have is a functor from category O to admissible representation, which is again almost categorically equivalent. In the sense that, so the irreducible maps to irreducible, if you send the irreducible representation to there, then it is either reducible or zero. And so this functor is exact, and so we know which irreducible representation sends to zero or something, and so yeah, basically we know most of the information about this functor. And again, so as in the classical case, we can get more or less the same result, like so. Classification of all admissible reducibles. And also the composition series of the admissible irreducible by the Varma modules, I mean, which is in terms of the category of, I mean, so we need a combinatorial argument, but if you really want to know this. Yeah. So far, so we are going really the same argument as in the classical case, and we still need to go a bit further. So, as I said in the classical case, at least this categorical equivalence doesn't give you any information about the unitarity. So, if you want to know unitarity of the admissible representation, you need another construction, which was the parabolic induction in the case of the classical case. And actually, we can define the parabolic induction also in the quantum group case. So if you recall the parabolic induction I introduced in the last time, so it was induced from the Borel subgroup, which corresponds to the upper triangular matrices in the SLN case. And actually, so we have a similar subgroup in the quantum group case as well, because so we are talking of this seen as the product of UQG, the compact part, and UQA plus n. And Borel simply means, so the upper triangular matrix simply means, so these elements are all upper triangular. We just restrict ourselves to consider the positive entries. And then we only need to take the intersection with the compact part together with the diagonal part, or the upper triangular part, which simply means the maximal torus. So maximal torus corresponds to the Cartan, which is just the subalgebra generated by the KIs. And then we merge with the O of KQ. So this should correspond to the algebra of the Borel. And then one can actually classify all of the one-dimensional representation of this, as in the classical case. So the one-dimensional representation of this Borel part is parameterized by, well, actually this is tensor product probably, yeah. Parameterized by, so the character, I mean, so basically, so the one-dimensional representation is parameterized by one-dimensional representation of this guy times one-dimensional representation of this guy, and one-dimensional representation UQH. So we should require a certain kind of integrality condition because so we need to get the integral, I mean the finite dimensional representation with respect to UQG action. So the character of this guy is simply the weight lattice, which simply corresponds to the dual of maximal torus. And we need to know the character on this, I mean the one-dimensional representation of this guy. And actually, this is also known to be, so basically, this is some, I mean, in the classical case, it was just the C-linear space, which corresponds to the dual of the Cartan. But we need to divide by certain lattice, actually, with certain parameterization, which is actually important in my talk, but something like this. And why this comes up? This comes from the fact that so when you consider the one-dimensional representation of KQ, actually this has to come from the evaluation at the point in the torus. So actually, notice that inside the UQG we have UQH. UQH is a kind of the group algebra over the Cartan. So basically, it's the Cartan part is a kind of uncompact. I mean, remains the same. And the same thing for the dual level. So the maximal torus lies in the q-deformation in uncompact. So this is just usual torus lies inside the q-deformation of the compact B group. And actually, all of the one-dimensional representation of KQ comes from evaluation at point at the torus. So this comes from the fact that the one-dimensional representation of KQ comes from the evaluation at the point in torus, but I mean we also need to consider non-unitary representation, so we need to complexify the maximal torus, which is same as this one with certain parameterization. So this is how this weird lattice comes into play. And I forgot to mention one thing in here. So basically, so also in the category O case, we have the period of the weight, which also gives you a certain period in this theorem. So basically, so we have a bunch of functors and category laws and kind of thing, but this only depends on your choice of lambda modulo pi I log q inverse q check or something. So modulo certain lattice with the imaginary direction. Okay, anyway, so this is something like this. And then, okay, anyway, so we know the one-dimensional representation of this guy, and then I want to induce the representation from this to the whole thing. And actually, one can do the more or less the same thing. I mean, induction is more like just taking tensor product over this. So, but if you want to, if we want to make a representation which is integrable, I mean, which decomposes into finite dimensional representation with this. So we need a bit of trick. So we consider, so we take again the dual, I mean dual of O of KQ. So we know what is the quantized enveloping algebra, and we know the coordinate algebra, and coordinate algebra is taken to be certain subspace of the dual of UQG, which simply means again, so UQG is, I mean, comparatively, UQG is the subspace of the dual of O of KQ. But then now we have another natural choice of the dual, which simply means, so this is, we have a Peter-wise decomposition, and then we take the corresponding direct sum of the endomorphism. So this is this. And actually, the algebra structure induced from the as a direct sum of the endomorphism coincides with the algebra structure induced from the dual, I mean the transpose of the coproduct. And actually, so this is an algebra, but this is an idea. And actually, so both inclusions are dense. So basically, so it's something like just replacing some functional algebra to another or something. Yeah, so yeah, basically something like polynomial algebras, the function each one is something. Anyway, so yeah, so we have two algebras, and one can actually form in the completely same way. We can form the quantum double of the OKQ with this another algebra. So this is actually again a star algebra, and which behaves more nice way in the operator algebraic setting actually. But anyway, so what I wanted to do is so again this is an ideal for the full quantum double. So especially this admits an action of this UQG, the double of UQG and OKQ. So in particular, we can restrict the action to here. So for each parameter corresponding to one-dimensional representation of the Borel, so each times each term is one can induce also we need to twist by a certain weight, as in the classical case again. So anyway, so if up to twist, so we can induce this to the representation of the whole algebra, and then this is a admissible representation of the whole quantum double, which we call the parabolic induction in the quantum case. So this is really the same as the parabolic induction in the classical. And now, so again, as in the classical case, we can give a precise description of this module in terms of this categorical equivalence. So if you send the Barma module by this functor, this is isomorphic to the parabolic induction with a certain fixed parameter like this. And using this, so we actually already know this parabolic induction has reducible subquotient with minimal k-type lambda. So reducible subquotient of LQ lambda with minimal k-type lambda exhausts all admissible reducibles and these two are isomorphic if and only if they are in the same while loop orbit. So basically, these two are a consequence of the theorem by Joseph and Dexter. So we need a bit more argument, but anyway, so this is just this is a consequence using this Joseph Dexter categorical equivalence. And what we know, as in the classical case also, is we have a linear pairing non-degenerate which is positive definite when you identify the underlying space, the underlying vector spaces of those positive definite with when one identifies Q of lambda nu to be this. So again, as you can see in the definition, as a vector space, OKQ part is redundant, so you can just omit this part. I mean, so this reduces to scalar. So what we get is only this one, which is a single space. Does not depend on the choice of your nu. So when you identify this in a canonical way, then this is actually positive definite. And again, this comes from, so in the classical case, this comes from the integration over the compact group, I mean compact Lie group, the maximal compact subgroup. And so we can do the same thing. So this basically follows from the Howe measure integration over the Howe measure on KQ. And another important thing is, so again, as in the classical case, so in the classical case, when I want to classify all the irreducible unitary representation, say SL of 3C, then the important thing here is the computation of the intertwining operator from here to here in the SU2 case. And this is also possible in the quantum case. So when K is SU2, then the only non-trivial intertwining operator is the intertwining operator from LQ lambda mu to the while group reflected, I mean the one reflected by the while group, I mean the intertwining operator, the meromorphic family of intertwining operators. So this is the only non-trivial intertwining operator, but this is given by certain formula, certain product formula, and we still have the same, more or less the same formula in the quantum case. And so actually we know what to expect. Basically, so the quantum group is defined just replacing certain numbers to Q numbers. And so this formula comes from certain product of not integer but numbers. And we only need to quantize those numbers. So to be precise, this is just for on given by on the new component in LQ. So what I say here is, so you decompose LQ lambda. Oh, so first of all, in the case of SU2, weight space or the curtain is one dimensional. So we identify this lambda or nu just as a number, where lambda is half integer and nu is arbitrary complex number. And so we decompose this module into VQ mu, with respect to the UQG action. And then, actually, for each part, this intertwining operator acts as a scalar, which corresponds to this scalar. Yes. And yes. So, and yeah, this is Q number. So Q number is something like this. And actually, the proof of this is, I will say, easier than the classical case, probably. So we already know there exists some intertwining operator. So what we need to do is only compute the intertwining operator. Existence is something we already know. And in the SU2 case, actually one can compute the K multiplicity, the multiplicity of VQ mu component inside the LQ lambda mu, and they are all one. So yeah, so all of, the reducible representation appears at most multiplicity 1. And then, of course, this map has to be equivariant with respect to UQG action. So we already know this is given by some scalar multiple on each component. And then what we do is basically just computing everything in terms of the generator. So basically, what we only need to know is the element of OKQ transforming each K type to the another K type. So this basically comes from explicit description of the commutation relation. The commutation relation of the model. So combining these, actually we can it is possible to classify all irreducible representation in the case of SU3 as in the more or less the same way as we did in the classical case. But for the higher rank case, as I said last time, we really needed the homological induction trick for the classical case, and I do not know how to do this in the quantum setting, but there is a way to avoid the use of the parabolic the homological induction. So what we observe from this bunch of results is, so first of all, so when you have a parameter. But at this moment, we do not divide by the lattice. So for a parameter, of course, the Hermitian form, so we know this has an Hermitian form, invariant Hermitian form, if and only if lambda nu is in the Y group orbit of this modulo 1 times 2 pi I equal to inverse. Yeah. So basically, this follows from this one and this one. But so we first ignore this modulo part. So we want to concentrate on lambda nu is really equal to y, really inside the Y group orbit of lambda minus nu part. So when lambda nu is in Y group orbit by this, then we have an explicit formula for the Hermitian form. And the Hermitian form is given by the intertwining operator with composed with the sesquilinear form defined as a whole. So this sesquilinear form is the one coming from the Howe measure. And this is the intertwining operator. Or from VQ lambda nu to VQ lambda minus nu part. And here what I want to observe is this part varies continuously with respect to Q. Just because this is Howe measure, and Howe measure so it is well known that Howe measure varies continuously with Q. Even you send Q to 1, so this is continuous. With respect to Q is between 0 and including 1. And also, this part is also continuous with respect to Q, including 1. Because we have the formula for this U2 case. So basically, this intertwining operator is given by, so this intertwining operator is parameterized by Y group element, and for each Y group element, you decompose this into simple reflections, and the formula for the simple reflection comes from this SU2 formula. So basically, the general intertwining operator can be written as a product of this type of the intertwining operator, and from the formula, one can show this converges to the classical case. So I'm not talking. There is a deformation of the algebra level, which converges, which this quantum double converges to the classical, a certain group algebra of the classical complex semisimple Lie group. But still, in the level of the intertwining operator, it is much more easier to show this varies continuously with respect to this parameter. And then, now, what I want to use is just an easy, elementary linear algebra. Just saying that also this Hermitian form has to be non-degenerate because the module is, this Hermitian form is invariant and the module is irreducible. So, And so the elementary linear algebra shows if you have a path, I mean, if you have a continuous path of the Hermitian form, which is non-degenerate, then if it is positively definite, if and only if, I mean, if it is positively definite at one point, if and only if it is positively definite at all points. So I want to use this. So plus elementary linear algebra. So if Yuki Arano has constant k multiplicities. I mean, so the positively definite forms, I mean, the Hermitian form has to be non-degenerate for all Q's, so it has constant. So this corresponds to this has constant k multiplicities. Along certain intervals. Then the induced the Hermitian form is positively definite if and only if it is positively definite at point 1. Then so this is positively definite if and only if this is unitary. If the classical case is unitary. And of course, the rest problem is this one. But this is something what we can know from Joseph and Lester. So basically, what we need to do is compute the composition series of the irreducible in terms of the Brahma modules, and it's possible actually. So this comes from Joseph and Lester. To know when this is the case. And so, yeah, so now I would like to conclude. Yeah, but actually this part is a bit tricky because when you have an imaginary part for the weight, then so when you look at the category O, then the degeneration of the irreducible module in the category O is determined from how integral this assigned weight is. And then now the presence of the periodicity in the imaginary direction in the category O shows at a certain point it might degenerate. I mean, it might be integral in a weird way. So actually, this does not give really the whole family of the irreducible representations, except that so we need the assumption where imaginary part of nu is sufficiently small so that it doesn't go over these integral points as q tends to 1. And I can explicitly describe when this is sufficiently small and this is sufficiently small, which means this does not pass the integral point where alpha is good. So if this is sufficiently small, then what I can show is this is unitary if and only if the classical case is unitary. So in the classical Lie group, which means not the exceptional one, so for type A to type D, we know all of the irreducible unitary representation of the complex semi-simple Lie group. So we know this result, and also for D2 and D and F. I'm not sure. yeah, we have algorithm to check it. Okay, anyway, this theorem reduces the unitarity of the representation of complex, quantized case to the classical case. And this in particular shows the property T for the quantum case because the trivial representation is when mu is really real, which does not have any imaginary part. So around the trivial representation, the representation category looks really the same. And also, so one can remove this assumption when the B group is type A. So when K is SUN, then this is unitary if and only if the twisted version is unitary for some. Or the reduced representation. So this. So yeah. So anyway, so I will write first. So there are a lot of. So this is another lattice, but so the only essential point is so the we can just divide by 2 pi L Q inverse Q check or something. So there's finitely many choice of this guy. And so actually, so this corresponds to the one-dimensional, non-trivial one-dimensional. So this corresponds to finitely many non-trivial one-dimensional unitary representation of the double. So basically, this simply says so up to the twist of this non-trivial one-dimensional representation, which does not exist in the classical case. So up to this, this is unitary if and only if the corresponding parameter is, the representation of the corresponding parameter is unitary. Okay, so this completes, so thanks to the theorem by Vaughan, this completes the classification of the unitary representation of the Drinfeld double in the type A case. And also, so our original motivation was to show property T for this representation category, and the property T can be seen as a kind of rigidity property for positive definite functions. So we also want to know some other property for the positive definite functions. And actually, from this classification, one can compute the positive definite function associated to this reduced representation, which is just extremal positive definite function associated to this. And we also know a formula to compute the positive definite function associated to this representation, which we call the spherical function. And actually, there's a close formula relating these two positive definite functions. So using this, actually, we can represent positive definite function over the representation category in terms of positive definite function over the complex semisimple Lie group. So basically, whenever you have positive definite function over representation category of SUQN, and then there exists a family of positive definite function K by invariant positive definite functions on Z, non-quantized, such that the function is given by a precise formula using this chi of lambda and chi dq to lambda plus 2 or something like this. So anyway, so we basically know everything in terms of the classical complex group. So yeah, so this is everything what I wanted to say. So thank you for listening, and yeah, I mean, thank you for coming for my lecture.
Any questions or comments?
So now that you have such a precise knowledge of this quantum double,
Yes.
Can you say anything about homology, cohomology?
Yeah, that's a good point. Yes. So basically, so what I originally concerned was, I mean, so basically we only know the behavior. So from this technique, we only know the behavior with the fixed central character. So you need to fix the central character. And so the fixing the central characters, the whole representation category can be seen as follows. So basically, so we have a base space which corresponds to the central characters. And then on the fiber direction, we have category O. So to know the irreducible representation, we can always fix the central character, and then you only need to look at the irreducible object inside category O. But if you want to know the cohomology or something, then the global torsion of this bundle is important. So what you get is only the certain spectral sequence corresponding to the bundle. So yeah, this still works for the SU2 case, but I mean for general, I mean so this is really non-trivial. But on the other hand, actually beforehand we can show something like, so when you look at the quantum double, the difficult point is this double cross product, right? I mean, so this is something very non-trivial construction, and then this does not behave well with the homology algebra. But actually, when I look at the when I look at the proof of the how I use the Joseph and Lester, actually I have shown that this is isomorphic to the cross product of this one. So actually, so UQG acts on here by adjoint action, and so this is actually really a cross product. So basically, in the cross product type of formula, one can reduce everything into the again the spectral sequence. But I mean, this part in this case, I mean, we can assume this part to be semi-simple. So this part just seems just says, I mean, you only need to take the invariant part. So this reduces the computation cohomology of this. And so this is actually up to localization same as this guy. So this reduces the computation cohomology of this, which is known. So basically in the trivial coefficient case, we can deduce every result only from the computation cohomology of the just quantized developing algebra.
Any other questions or?
Just for curiosity, is there any non-admissible representation?
Yes, should be, but yeah, it's a bit tricky to ask. I mean, what is a non-admissible representation? I mean, so yes, I mean, so of course, if you just look at all of the algebraic representation, then there's a lot of non-admissible representation. But so for example, you can also restrict ourselves to the representation of Banach space or something, which is uniformly bounded or something. And then it might be possible that you can also find admissible, non-admissible Banach space representation, which is known in the classical case by Zolgel, I guess. Yeah, but I mean, so I don't know. I mean, I haven't worked on that. Yeah, probably yes.
Nothing else, so let's thank the speaker again. Yeah, there's biscuits and coffee and tea in the main building.
Yeah, but actually, so the computation of the epistemology of this is done when the Q is transcendental. But actually, there is no explicit construction of the resolution. So this only gives the computation of the cohomology of the trivial coefficient, but not the others.
Can you deduce petty numbers, for instance?